Hello, my name is Naimajori, and welcome to Lab 3, Black Holes. So this lab is composed of two main parts. Part 1 is trying to figure out the mass of a black hole by analyzing a star's motion, and Part 2 is using that calculated mass of the black hole to figure out the initial velocity that a spacecraft must have to get close to a black hole and leave the system without crashing into the planet or the black hole. And hopefully this lab will demonstrate Newton's second law and its relationship with momentum. And just a quick preview of the results, I got the mass to be this, and the ship speed to be this. So let's get started with part 1, finding the mass of the black hole. Alright, let's talk about some fundamental physics. First up, Newton's second law, which states that the net force on a system is equal to the change in momentum over change in time. Well, if the change in time is so small, let's just use the derivative of the momentum. Well, let's expand this using the product rule, and we can figure out the parallel and perpendicular components of the force in terms of momentum. Well, in our lab, we have the star as a system, and the surroundings in this case is going to be the black hole. And the force between them is the gravitational force, which is equal to this equation right here. Well, if we rearrange this, we can figure out the mass of the black hole in terms of the momentum of our star. Alright, so in order to get a very accurate measurement for the mass of the black hole, we need to know how the momentum of the star is changing at multiple instances around its orbit of the black hole. Now, this would be a great hassle if I just sat down and hand calculated each individual change in momentum. So thankfully, I'll be using a GlowScript computational model to do this for me. So I went in and inputted the initial conditions of the star, and then here is how the velocity, the x and y component of the velocity of the star, will be calculated at every given timestamp. All right, so here's just a couple more computational steps I had to go through in order to find the parallel and perpendicular components of the momentum in order to find the net force acting on our system, which is the star. Now, the most important line I would say is this last one right here. Here we can finally calculate the mass of the black hole at each given time increments by using this change in momentum over time, or this net force that we calculated, times the distance between them squared over gm. This animation is a good representation for our simulation. Dang, those rhymes went crazy. Anyway, here we have our star orbiting our black hole, and shown are the components, the parallel and perpendicular components of the net force. The orange is just the sum of that. Well, since the orbit is not circular, we're going to have different net forces on the star. When you're closer to the black hole, the force is going to be greater. Now, because of this, we had to calculate the mass at each individual timestamp. So we got the average mass from all those different masses, and we got that calculated to about 1.5 times 10 to the 34th kilograms. Part 2. Don't crash. All right, so just to restate, what we're trying to do right here is figure out the initial velocity of a spaceship so it doesn't crash with the planet or the black hole. Now to do this, we're going to be doing some more coding. So up here, I'm going to put in the mass from our black hole from part 1, and here are some more constants that we know. Now up here, I'm going to put the initial planet speed and velocity, and down here is through trial and error, we're going to figure out what the initial ship speed and velocity is. All right, another huge chunk of code, but basically what we're doing is isolating our system and figuring out all the net external forces acting upon it. So here we go, the planet is our system, acted upon the black hole and the ship, and we're calculating the forces using our beloved equation of universal gravitation. There's another rhyme for you right there. All right, and then our next system's the ship acted upon the black hole and planet, and the reason we're doing this is to figure out the motion of both of our systems over time. So we're basically iterating the position and velocity using the net forces. All right, so after the multiple trial and errors in order to find the speeds, we finally got this graph that shows the spaceship leaving the system successfully. There you go. What are some errors or limitations in this lab? Well, first up, we use a lot of approximations. Since this is just a simulation, it won't really represent reality, since there's so many other external forces or factors that could affect our system. And next up, we have accuracy. Since we use trial and error, that's not that accurate. There could be way more precise velocities that could get the spaceship even closer to the black hole. All right, well, what does all this even mean? And how is the net force and its parallel and perpendicular components different from the rate of change of momentum and its components? Well, here's the formula. The net force is equal to the change in momentum over change in time. So mathematically, they're the same thing, but one is easier to measure than the other. The net force, you need to know every single outside factor playing a role in exerting a force on our system, and that can be crazy to calculate. But for the rate of change of momentum, all you need to know is the system's change in velocity or motion. Now, what if the initial velocity of the spaceship needs to orbit around the black hole? Well, through trial and error, here are the speeds. And in this case, the magenta is the orbiting of the spaceship around the black hole. There you go. Thank you so much for your attention and have a great day.